Let's jump right into one of Europe's most fascinating and frankly frustrating engineering paradoxes. It's a conflict we're calling the Kirchhoff clash. Basically, we're going to explore exactly why physics, time and time again, completely defeats market economics on our energy grids.
The core of this whole conflict really boils down to one simple truth. Electricity absolutely does not care about financial contracts. It only cares about physics. Think about it. We have these incredibly sophisticated AI algorithms that clear financial markets flawlessly. But power itself, it refuses to follow commercial agreements. You can have the most perfectly balanced financial ledger in the world, with traders agreeing on exactly who buys what. But the actual electricity doesn't get a memo. It quietly obeys two simple equations developed almost 2 centuries ago by Gustav Kirchhoff. And just like that, the market's perfect economic solution becomes physically impossible.
So, what we're really looking at here is a heavyweight bout between economics and physics. On one side, the market decides who owns the electricity, and its only goal is to optimize for cost. It just wants the cheapest power to reach the buyer. Simple, right? Well, on the other side, we have the grid. The transmission system operator has to optimize for physical delivery and feasibility, and those are definitely not the same things. In most industries, once the price settles, you're done. But electricity adds a whole other layer. The physical grid has to satisfy strict physical constraints, like thermal limits so wires literally don't melt, and voltage stability to keep the entire system from just collapsing. The market solves one problem, but the grid has to solve a completely different one.
To understand why this massive disconnect happens, we have to look at how economists actually view the grid. They love this idea called the copper plate assumption. Basically, market models treat an entire country, let's use Germany as an example, like one giant bathtub. The theory is that you can inject electricity anywhere, pull it out anywhere, and the pressure remains exactly the same, everywhere with zero constraints. It makes for a super simple market equilibrium. One price, one market. It's elegant, it's simple, and, well, actually scratch that. This beautiful illusion is fundamentally wrong.
Because, as it turns out, physical reality looks nothing like a copper plate. To put it in perspective, Germany's actual grid is made up of over 35,000 kilometers of complex, alternating current transmission lines. We're talking enough wire to wrap almost all the way around the Earth. Plus, you've got thousands of substations and highly volatile background forces, like reactive power, that are constantly needed just to keep the grid dynamically stable. In a real physical network, every single megawatt injected at point A changes the flows literally everywhere else. You just can't simplify geography away. The market might pretend the system is simple to make trading easier, but physics never, ever simplifies.
And this brings us to this absurd geographic tension that practically breaks the market. Up in northern Germany, you have these massive offshore wind farms injecting enormous quantities of electricity into the grid. It's an incredible feat of renewable generation, truly. But the demand? The heavy industry that actually needs that power mostly sits hundreds of kilometers away in the south, in places like Bavaria. So the market says, awesome, let's sell this cheap wind energy to the south. But then physics steps in, kind of like a bouncer at a club, and says, hold on a minute, the transmission corridor to get it there is already totally full.
Let's walk through how a breezy Sunday afternoon can escalate into an absolute crisis. First, demand is relatively low, and those northern wind farms are spinning at max capacity. Second, because that power is so cheap, wholesale prices drop, and the financial markets celebrate a perfect, highly efficient transaction. Everyone's happy, right? Well, then we hit steps 3 and 4. When those electrons actually start moving south to fulfill those perfectly cleared contracts, they blindly follow physical impedance, basically electrical resistance. The result? The physical grid bottlenecks, and transmission lines completely overload. The market's solution was economically flawless, but physically, it was a disaster.
Which brings us right back to the supreme ruler of the grid. Alternating current doesn't map out routes like delivery trucks on a highway. You can't just divert electrons to an empty side street when there's a traffic jam. They distribute themselves automatically according to Kirchhoff's laws. They completely ignore whatever financial deal the traders struck. They just divide among parallel paths, creating massive congestion. Sometimes, these rogue electrons will even hilariously spill over the borders into neighboring grids, like Poland or the Netherlands, just to eventually loop back into southern Germany. It's wild. But this is exactly why physics defeats market economics. Physical delivery depends entirely on the actual network topology, not the financial contract.
So what happens when the market essentially breaks the grid? Enter Redispatch 2.0. When those transmission lines overload, grid operators have to step in and apply this incredibly expensive band-aid. They basically have to pick up the phone and order wind farms in the north to just stop producing power. Power, by the way, that the market had already bought. Meanwhile, they have to tell gas or coal plants down in the south, which the market had originally rejected for being way too expensive, to fire up just to keep the lights on. The generation moves, but the demand doesn't. Millions of euros change hands, and those costs, yeah, they show up directly on your utility bill. Not because electricity itself was scarce, but simply because physics demanded it.
Now, historically, this kind of redispatch only involved a handful of massive coal or nuclear plants. But today, with renewables, the complexity has just exploded. Imagine trying to conduct a symphony orchestra with 50,000 musicians. You've got small wind farms, solar parks, battery systems, biogas, and you have to simultaneously rewrite their sheet music every 15 minutes. That is the immense, mind-boggling operational chaos of Redispatch 2.0. Grid operators are constantly juggling changing weather, fluctuating demand, forecast errors, you name it. The system functions, sure, but it does so at an absolutely staggering administrative and financial cost.
And here is the uncomfortable truth that policymakers are really struggling to grasp. You can pass all the European regulations you want. You can tweak market rules and compensation schemes until you're blue in the face, but no parliamentary vote is ever going to rewrite Ohm's law. No market directive can override the conservation of energy. Physics remains completely sovereign. One discipline, economics, is trying to optimize incentives. The other, engineering, is strictly obeying the laws of nature. And when those two clash on the grid, Kirchhoff always wins, hands down. This directly leads us to one of the most intense structural debates in the energy transition right now: how we price electricity. Germany currently uses what's called a uniform price, a single bidding zone. Think of it like this. It's as if an airline ticket costs the exact same amount whether you're flying out of a totally empty airport or one with a massive runway backup. That uniform price completely hides the actual scarcity. Consumers in the south don't see the delivery constraints, and generators in the north are blind to the transmission congestion. On the flip side, you have nodal pricing. This approach actually forces the financial market to finally respect those physical bottlenecks by changing the price based on location. It makes the congestion visible, finally forcing the economics to merge with the physics.
Now, to be fair, Germany isn't just throwing its hands up and letting the grid fail. They are actively engineering their way forward. We're talking about building massive high-voltage direct current corridors. Think of them as giant electricity superhighways designed to move vast amounts of power. They're also deploying advanced grid-forming inverters to stabilize the system and using AI and dynamic line rating to squeeze more capacity out of existing wires based on real-time weather. And of course, they are rolling out massive battery storage systems and demand-side flexibility. Every single one of these innovations is a huge step. But none of them eliminates the underlying reality that electricity must, first and foremost, obey physics. Which brings us to our final critical takeaway for this explainer. As renewable energy continues to scale up and decentralize, this gap between commercial trading and actual physical electricity flows, it is only going to get more obvious and significantly more expensive. Redispatch 2.0 isn't a failure because it exists. It exists because our current markets completely fail to represent the physical electrical network. So we really have to ask ourselves, are we going to keep applying these billion-euro band-aids after the market clears? Or is it finally time to redesign the core rules of the game to respect the undisputed champion of the grid, the laws of physics? I'll leave you with that thought, because how we answer that question is going to shape the entire future of our energy systems. Thanks for tuning in, and I hope this changes the way you look at the power keeping your lights on.